Welcome back to Brief Physics channel. In today's video, we will take a closer look at the concept of linear momentum and also the conservation of linear momentum. Let's assume you have an object whose mass is m kg, and it's moving with some velocity v meter per second in some specified direction. We say this object has linear momentum, and the linear momentum is defined as follows. It is the product of that mass m in kg times that velocity in meter per second. So you can clearly see that linear momentum is a vector quantity. The direction of that linear momentum is the same as the direction of the velocity in that direction. The SI unit that we use to quantify linear momentum is kg meter per second. So you see, in order for an object to have linear momentum, it must be moving with some velocity. So that means no motion, no linear momentum. As simple as that. Now let's look at the principle of conservation of linear momentum. Let's assume the momentum of this object changes in certain amount of time, delta t. Delta p, as we know, is quite simply delta of mv. Delta here is chosen to represent the change. Because mass is a constant, it can be taken out of that delta sign, and you get m delta v. So delta p, the change in momentum, is quite simply the mass times the change in velocity of the object. So we can simply write m delta v over delta t. This quantity right there is just the acceleration of the object. So we can write the change in momentum with respect to time equals mass times acceleration. And now we in turn know that acceleration is related to some kind of net force. So ma is net force, that is Newton's second law. What that means is, if this object is moving between 2 points, let's say point 1 and point 2, and its momentum does not change, so that means delta p is 0. All this argument forces us to conclude that there should not be any net force acting on the object as well. So if you want the momentum of an object or a system to be a constant, namely if you want the momentum of the system or the object to be conserved, then that system or the object should not be subjected to any kind of net force or an external force. Only then its momentum will be conserved. Another way to write delta p equals to 0 is by simply to say that the linear momentum, say in point 1, equals the linear momentum of that object at point 2, provided there is no external force acting on this object. This statement is what we called the principle of conservation of linear momentum. Let's come back to this diagram, where you have one object moving from point 1 to say point 2. Let's assume at point 1 it has a speed of 10 meter per second, and this object is moving under the influence of some friction between the surface of the object and the surface of the floor on which it is moving, kinetic friction. And that friction causes this object to come and stop there. So at that point 2, its velocity is 0 meter per second. So you can obviously see the change in velocity. Namely, it is 0 I hat minus 10 I hat meter per second, which is minus 10 I hat meter per second. Because there is a change in velocity, there must be also a change in linear momentum, and therefore, in this case, the momentum or the linear momentum is not conserved. It is not conserved because of the presence of this external force in the form of friction. That is the essence of conservation of linear momentum. Let's look at the following problem. A 1800 kg truck traveling initially north at 10 meter per second turns east and accelerates to 15 meter per second. find the change in truck's kinetic energy and also the change in truck's linear momentum. The aim here is to highlight the fact that linear momentum is a vector and kinetic energy is not a vector. So that would affect the way the calculation is done for part A and for part B respectively. So let's look at the system. So you have a truck that is initially moving northward like that, 10 meters per second. And at a later time, it is moving east with a speed of 15 meters per second. So let's first calculate the change in kinetic energy. The change in kinetic energy is the final kinetic energy minus the initial kinetic energy. Now the final kinetic energy is half times the mass, which is 1800, times the final speed squared. So the final speed is 15 meters per second, square that, minus half times mass 1800, initial speed squared. Initial speed is 10, so square that, and that's going to give you the change in kinetic energy. And that's going to give you 112,500 joules in the change of kinetic energy. So part A, the answer is 112,500 joules. Now let's try to calculate the change in the truck's linear momentum. Now linear momentum is a vector, so we have to be careful here. The change in the linear momentum is the final momentum minus the initial momentum of that truck. So the final momentum, that part of the motion, equals the mass of the truck 1800 times its velocity at that time, which is 15 I hat. I'm using I hat as a unit vector along eastward direction. And then Pi, the initial linear momentum, again equals to its mass times the initial velocity, which is 10 j hat. Now j hat is a unit vector along the northward direction, which will give you 27,000 I hat minus 18,000 j hat in the unit of kg meter per second. This line gives you the change in linear momentum in vector notation. Now let's calculate the magnitude of that momentum change, and that is pretty simple. It is 27,000 squared plus 18,000 squared. Well, it's actually plus minus 18,000 squared, square root, and that's going to give you 32,450 kg meter per second for the magnitude of the change. What about the direction of this change? Now let's look at the vector notation. It has 27,000 in the I hat direction and 18,000 in the minus j hat direction. So we need to calculate that angle, and that angle would give you the direction of the change. So from the diagram and trigonometry, we know alpha is arctangent of 18,000 over 27,000, and that's going to give you 33.7 degrees. Because the direction of the change is like that, we say it is 33.7 degrees south due east. You see how it is straightforward to calculate the change in kinetic energy compared to calculating the change in linear momentum, just because kinetic energy is a scalar and linear momentum is a vector. Problem 2. An object at rest at the origin of an xy coordinate system disintegrates into 3 pieces. So let's assume that is the object, and that is the xy axis. Initially it is at rest, 0 meter per second. Just after disintegration, piece 1 with mass m moves with a velocity minus 20 meter per second I hat. So piece 1 is moving like that, mass m, and the speed is 20 meter per second in that direction. We assume that this is the x-axis and that is the y-axis. Piece 2, also with mass m, moves with velocity minus 20 meter per second j hat. So piece 2 is moving like that, 20 meter per second, the mass of which is also m. The third piece has mass 2m. So the question is, just after this disintegration, what are the velocity of the third piece? So the third piece is moving somewhere. We don't know where. The mass is 2m. We want to know the velocity of that third piece. What we have to do here, we have to apply the principle of conservation of linear momentum. Conservation of linear momentum says the initial momentum of the system must be the same as the final momentum of the system. Initially, we know the object is at rest, so there is no velocity. That means its linear momentum is also identically zero. So if momentum is conserved, namely if there is no external force or net force acting on this object, then the final momentum must also be zero. By the final momentum, it consists of three parts: part 1, part 2, and part 3. Part 1, with mass m and velocity is minus 20 I hat. Part 2, also mass m, the velocity is minus 20 j hat. And part 3, the mass is 2m, velocity we don't know. We want to determine that. So you see on the right, all the terms have mass m in the terms, so they will just go away. And immediately we can solve for the velocity of the third piece, and that's going to be 20 I hat plus 20 j hat over 2. And that's going to give you the final velocity as 10 I hat plus 10 j hat in the unit of meter per second. So there you have it. The velocity of the third piece would be something like that, given by that expression. The magnitude of that velocity is 10 squared plus 10 squared square root, which is 14.14 meter per second. Now what about the direction? The direction can be expressed by expressing this angle alpha. Now we know that the velocity is 10 I hat and 10 j hat. So alpha is given by arctangent 10 over 10, arctangent 1, which is 45 degrees. So the direction of the velocity of the third piece is 45 degrees above the positive x-axis. And that completes the problem. Thank you for watching.